I'm Chuck Newell from GSI Environmental.
And I'm Dave Adamson, also from GSI Environmental. This is one of a series of videos that highlight cutting-edge CERDIP and ESTCP R&D efforts.
Now today we're talking about an emerging contaminant, 1,4-dioxane, and learning about how it behaves in groundwater.
That's right, Chuck. So let's take a look at what we're going to cover in this video. The real problem is that 1,4-dioxane is a relatively new addition to our monitoring programs at contaminated groundwater sites. So there's simply not a lot of empirical data on how it behaves in the environment. If your job's getting a site cleaned up, you really don't have that much information maybe to rely on.
And that was part of the focus of a CERDIP-sponsored project titled In Situ Treatment and Management Strategies for 1,4-dioxane Contaminated Groundwater. Now, Dave, I know you were the PI in this project. I've also been working as a co-PI, along with a great group of researchers like Shayla Mahindra at UCLA, Michael Wong at Rice University, and Dan Bryan at GeoCleanse.
Now, the overall objectives of this particular project were to build a better conceptual model for how 1,4-dioxane behaves in the environment so that we have a more informed basis for managing these sites. We accomplished this through a combination of big data studies, lab-scale treatability tests, including those that involve treatment trains, and then we collected field data at dioxane-contaminated sites.
Okay, now we can't cover everything from this project today, but here are a few of the key points from the work we've completed so far. First is that there's a lot more evidence for shorter plume size than maybe we feared based on dioxane's properties.
And second, there's a lot more evidence for attenuation of dioxane relative to what we might have expected.
And finally, other processes like matrix diffusion should be accounted for when you're trying to manage these sites. In short, we've just got a much better conceptual model than when we started. So let's take a closer look at 1,4-dioxane to help define the nature of the problem. Now, as a groundwater contaminant, it's a big deal because it was used as a stabilizer for 1,1,1-trichloroethane, right, Dave?
Yeah, that's right. Now, I've got a couple structures here drawn out. How about a little quiz for you to start off with, Chuck? What's that first compound there?
Okay, that's the big guy. That's what we're talking about, 1,4-dioxane, the subject of this video.
And then second?
That's 1,1,1-trichloroethane.
Yeah, and we've got that included here because 1,4-dioxane was used in formulations of 1,1,1-TCA to improve its stability as a solvent. So you'd expect them to co-occur. We got one more compound here, Chuck. What's that one?
Got the double bonds. That's trichloroethane.
All right, exactly. 3 for 3 on this quiz. The thing to remember about TCE is that it may have been the first solvent used at a lot of these sites. And then there was maybe a move to phase it out due to occupational health concerns, followed by a switch to other solvents like 1,1,1-TCA.
So a lot of these sites where chlorinated solvents and their degradation products are present, there's a strong likelihood that dioxane is present too. And we've got a lot of data to support that.
But a problem is that dioxane may not have been included in the monitoring program at these sites yet. And dioxane also has been considered a pretty persistent compound.
Yeah, and it's also highly soluble in groundwater, while it doesn't strongly sorb to aquifer material.
So that's led to this concern that at sites where you've got a chlorinated solvent plume formed, there may also be a dioxane plume that has been sort of racing out ahead and creating a much longer plume.
Okay, and that's one of the hypotheses that you wanted to test, and you wanted to use actual monitoring data to figure out what was happening at these sites, right?
Yeah, so what we did is we performed a big data study using databases like GeoTracker in California, and we developed a method to estimate relative plume sizes. So in this case, we were able to get estimates from just over 100 sites with dioxane, and maybe the easiest way to show what we found is to go back to that cartoon of the co-occurring plumes.
Okay, now what percentages of dioxane sites fell into this category you already drew, where the dioxane plume is longer than the chlorinated solvent plume?
Okay, so that's the one at the top, and again, that's the one we assumed that would be the most common. Well, it turns out that only 21% of the dioxane plumes were really longer than the chlorinated solvent plumes, really far from the majority that what we expected to see. At another 23% of the sites, the dioxane plumes were about the same size as the chlorinated solvent plume.
Okay, and I can do the math, so that means that at the remaining 56% of the sites, it was actually the chlorinated solvent plume that was longer than the dioxane plume. Definitely different than what we'd expected based on dioxane properties. So why is that?
Well, for the most part, it was really 1,1-DCE and TCE that were longer, not TCA. TCA turns out is attenuated fairly quickly. And remember that TCE was typically the first chlorinated solvent used at these sites, and it may have had a couple decades head start on dioxane, which was more associated with TCA releases. So dioxane plumes do have a chance to catch up, but at least right now the data are telling us that most of them are the same or shorter.
So that's plume size as an example of the scale of the problem. Now let's take a look at dioxane attenuation. What did you find out?
Well, we were teaming up with Hunter Anderson at the Air Force, who's another expert in 1,4-dioxane. And we're trying to look at attenuation in a couple different ways. First, we estimated source attenuation rates at all of the geotracker sites and determined which one of these were statistically significant. That's what's shown in this histogram with the frequency distribution of the dioxane half-lives on the y-axis.
And then you did the same thing with the Air Force sites?
Well, Hunter did the analysis on the Air Force data, and he was using monitoring well data instead, mostly because it can be really hard to classify Air Force installations as individual sites. But in both cases, we were able to establish that significant dioxane attenuation was occurring at a meaningful number of locations. Certainly not at all sites, in part because we had to set this statistical significance threshold, so that knocked out a lot of sites in the GeoTracker database that had relatively short monitoring records. But we were able to establish that on a site-wide basis, we had a median dioxane half-life of 20 months for 22 sites. And at individual wells on that right panel, the median value for these 131 wells corresponds to a half-life of 48 months. And these end up being pretty meaningful half-lives if you're considering site management with natural attenuation, which you're worried about sort of decades or more type behavior.
Now, I know that you also looked about how dioxane attenuated relative to the chlorinated solvents at these sites too.
Yeah, and it turns out that for the GeoTracker data, the dioxane attenuation rate tended to be similar to the attenuation rates for TCE and 1,1-DCE, or at least difficult to distinguish statistically. The TCA rate, typically much faster, and that matches what we'd expect to see.
Okay, so the bottom line is that the dioxane attenuation rates were not that different than those of several of these important co-occurring contaminants.
And one other important point to make is that dioxane attenuation rates could be positively correlated to the presence of oxygen and negatively correlated to high concentrations of chlorinated solvents and metals. Now, these are the same conditions that we'd expect based on all that great lab work that's been done at places like Rice University, UCLA, and other labs. And they've shown that these are important parameters for biodegradation. One example is that the presence of oxygen is important because all biodegradation pathways identified to date for dioxane are aerobic, not anaerobic. Shayla Mahendra at UCLA, she's demonstrated that the presence of 1,1-DCE and several other chlorinated solvents inhibit these biodegradation reactions for dioxane. And we also see inhibition noted with several metals such as cadmium or copper when they're present at elevated levels. So the field evidence from our project, it's definitely consistent with the lab evidence, and it suggests that biodegradation is playing a role for dioxane.
I think this is a really important point, that there is evidence that biodegradation is a viable way to treat 1,4-dioxane. This is another area where we've been changing that old conceptual model for this compound.
Right, and there's been this increasing evidence in these lab studies that 1,4-dioxane can be degraded aerobically. These researchers are showing aerobic organisms that can degrade 1,4-dioxane as a carbon source, as well as other organisms that degrade it co-metabolically in the presence of a co-substrate like propane. For treatment, this is important in two different ways. First, the potential for natural attenuation can be assessed because there are biomarkers for these organisms that can be measured in environmental samples, so that gives you a strong line of evidence for M&A. Second, it points out that enhanced bioremediation using amendment injection or even bioaugmentation, that may be an option at some sites if there's a need to speed up this dioxane mass removal.
Okay, it's not going to be the same design that works for chlorinated solvents, which are mostly degraded anaerobically, but maybe as an add-on, like what's shown in this cartoon. This is a sequential anaerobic-aerobic in situ treatment process.
Yeah, that's one way to do it. Another option that this project looked at is in situ oxidation to treat the chlorinated solvents, followed by bioaugmentation in the same aerobic conditions. We've shown that these 1,4-dioxane degraders, they do great as sort of a second step, and this is a treatment train that could really be effective for 1,4-dioxane.
So, okay, in terms of plume footprints and the potential for attenuation, the dioxane problem is maybe not quite as bad as we may have guessed without these data. Maybe next we look at the impact of matrix diffusion on dioxane, fate, and transport?
Yeah, we know that matrix diffusion is a big issue for chlorinated solvents based on some great recent research, a lot of it sponsored by CERTIP and ESDCP. And this matrix diffusion issue, what we know is that it can really enhance the persistence of these compounds. I think this diagram illustrates the reasons why. So you can think about an aquifer maybe overlying a low permeability zone, something like a clay or a silt where there's little advection. You've got the source released up there in the higher permeability or transmissive zone. While that source is present, you see a loading of that lower permeability zone based on the diffusion process. So contaminants end up moving based on a concentration gradient, pushing material via diffusion into that low K zone.
So once that source is depleted, you've essentially reversed the concentration gradient. And now all that mass that diffused into that low K zone, it has the potential to back diffuse into the aquifer and sustain the plume for a long period of time.
In our CERTA project, we attempted to model a typical dioxane release scenario to see what would happen.
And this was accomplished using the Matrix Diffusion Toolkit, a free software tool that was developed for ESDCP by Colorado State University and GSI. Dr. Shala Farhat at GSI was the principal designer of the tool.
And in this case, we wanted to simulate TCA and dioxane being released at the same time. We had to define a loading period and a representative concentration during this loading period. It turns out that dioxane would be predicted to be present for just a few years. So our scenario, we started out in 1970. Dioxane was essentially depleted from the high permeability parts of the source zone within 3 years. But that doesn't really mean it's gone from everywhere. So we put together a movie to show what happens. So Chuck, get your popcorn ready and I'll hit play.
Okay, well I guess I forgot the popcorn, but don't let that stop you. Go ahead.
Here's our modeling domain. We're looking at a 2-layer model with sand on the top and our low-K silt or clay below. We have depth on our y-axis and distance down gradient on the x-axis. We're going to release this source up in the transmissive layer, and remember that it only lasts for a few years in the case of a dioxane release.
And what we're really interested in is what's happening in this low K zone. While the source is present, you get diffusion in. When the source is absent, you get diffusion back out. We've got our color-coded key for concentration out at the bottom. High concentrations are red. We also track the percentage of mass in low K zone on the bottom right.
So we're going to start off with our release in 1970 and show what happens each year for 80 years. So right away you see that there's this huge amount of mass, those bright reds being pushed into the low K zone. We're already up to 1982 and you've got more than 70% of that mass in the low K zone. A few obvious things are going on here. First, even though the source was gone in 1973, there's still a significant concentration gradient that pushes mass deeper into the low K unit. Second, even though the source on the left-hand side was depleted pretty quickly, you saw the remnant move down gradient to the right and contribute to diffusion into the low K zone as the plume expanded. And if you were looking at that number in the lower right, that mass in the low K zone, it jumped up really quickly, but then it didn't really change much after that. Mass was diffusing out, maybe near the source zone after the source was gone, but that was being balanced by mass diffusing in farther down gradient. So in terms of the overall mass in the low K zone, we're seeing a pretty stable situation, even 80 years after the release. Still a lot of red in the source. Those are concentrations above 100 milligram per kilogram, and yellows throughout an area 300 meters down gradient and 2 meters into the clay.
So clearly this could enhance the persistence of the dioxane plumes. Is this a concern at most sites?
Well, there's definitely a sense that the geology and heterogeneity at sites is a lot more important than maybe we'd originally assumed. And that's what we're showing here in this example of a hydrostratigraphic profile from the hydraulic profiling tool, where you're getting an estimate of the hydraulic conductivity as you advance this tool deep into the ground. You can see that there's a lot of heterogeneity in the permeability, and these differences in permeability can lead to a lot of mass storage. This ends up being really important because it's less practical to attempt aggressive in situ treatment if a site is dominated by the mass in the low K zones. Now we've seen evidence for this at some sites, though it's not necessarily universal. In this particular project, we're documenting that there's a lot of dilute dioxane sites, suggesting that there is no real source zone left, but maybe the source is this mass that's diffusing from the more stagnant zones. So I think that at a minimum, matrix diffusion should be a concern that needs to be investigated and included in a site-specific conceptual model.
Okay, well that sounds great. So let's wrap up by revisiting our key points. First, we saw the results that suggest that there's some good news in terms of dioxane plume sizes.
Right, and the implication of this is that maybe it's less likely that the dioxane plume extends way beyond the existing monitoring network that was probably being designed for the chlorinated solvent plumes.
And also, there's evidence for attenuation at some sites.
And that really enhances the potential viability of M&A and biodegradation-based remedies.
And then we finally saw that matrix fusion could be an important consideration in how a site is managed.
That's right. And so when you think about these results in terms of sort of an improved conceptual model, they do suggest that at some sites, conventional treatment might not be all that feasible, and other strategies like natural attenuation through biodegradation or containment might be more appropriate options for longer-term management of dioxane.
Okay, well thanks Dave, and here's where you can go to find more information about this great CERTUP project on dioxane. And remember, this is just one of a number of videos highlighting key results from different CERTUP and ESTP research projects. Just go to YouTube and search CERTUP ESTCP micro lectures to see more of these.